All right, class, the last thing I want to talk about is complex numbers. So, complex numbers come about when we're taking the square roots of negative numbers. And we define the imaginary unit I as a square root of negative 1. And because of this, I squared is negative 1. Remember, if I take a radical times a radical, you're going to get what's left underneath. Like the square root of 2 times the square root of 2 is 2. So this would give you negative 1. Okay? We say I is the principal square root of negative number. So for any real positive number, b, if I have the square root of negative b, we always want to pull out the square root of 1 first, okay? And multiply that by the square root of b. That was a typo. Why is it important to pull out the negative first? Well, remember, when you're working with radicals, you can break them apart into their factors. So, for example, the square root of 6 is the square root of 2 times the square root of 3. So we could rewrite this as the square root of negative 1 times the square root of 100. That's going to give you I times the square root of 100. The square root of 100 is 10. But we don't want to write I10, right? That looks really funny. We like to kind of treat this a little bit like a variable. So we're going to want to write this as 10I. Okay, so let's practice that again. If I have negative the square root of negative 36, I'm going to have negative I square root of 36. You can write out every step if you wish, but I'm going to just go ahead and pull out that I. So now I have negative I square root of 36, which is 6. So I'm going to write this as negative 6I. Let's go ahead and do this again. That should be a B. I have the square root of negative 2, which is square root of 2 times I, so I square root of 2. In this case, I have I square root of 54. Well, 54 factors into a 9 and a 6. 9 factors into a 3 and a 3. So I can pull out a factor of 3. So that gives me I times 3 square root of 6, which would be 3I square root of 6. So the order we're going to want to put these in is whole number or rational number part, imaginary part, then radical. Okay? Now, when we're multiplying complex radicals, we always pull out the I first. We have to pull out the I first. I can't just multiply negative 4 and negative 8. It's going to completely eliminate the fact that we were imaginary, right? Because two negatives make a positive. So now I have I square root of 4 times I square root of 9, which gives me 2I, because the square root of 4 is 2, so 2I times 3I, which gives me 6I squared. But remember, I squared equals negative 1. So I have 6 times negative 1, which is negative 6. All right, let's go ahead and work on this. I have I square root of 3 times I square root of 7. If I multiply these together, this gives me I squared, because I multiply my i's, and then I multiply what's under the radical, the square root of 3 times 7. So I have I squared, square root of 21. The square root of 21 cannot be simplified, but I squared can, because I squared is negative 1. So I have negative square root of 21. Let's take a look at this again. If I have the square root of negative 2, that's I square root of 2 times I square root of 8. Square root of 8 can be simplified, right? 8 factors into a 4 and a 2 and a 2 and a 2, so I can pull out a factor of 2. So now I have I square root of 2 times 2I square root of 2, because I pulled out this factor of 2. Now I have Square root of negative 5 times the square root of 6. So I have an imaginary number times a real number. And then I can do this. I square root of 5 times the square root of 6 equals I square root of 30. 30, although it seems like it should be able to be simplified, is 3 times 10, which is 2 times 5, so there's no factors in common. So my final answer is I square root of 30. And I didn't finish the problem above, did I? So that gives me 2, if I come back here to refresh, I have I square root of 2 times I square root of 8 equals I square root of 2 times 2, because I could pull a factor of 2 out of our radical, 2I square root of 2. I multiply my coefficients, so that gives me 2I squared. I multiply what's under the radical, that gives me the square root of 4. So now I have 2 times I squared, which is negative 1, times the square root of 4, which is 2. So 2 times negative 1 is negative 2. Negative 2 times 2 is negative 4. Final answer. If we can multiply complex numbers, we can most certainly divide them. So again, the first thing we want to do is pull out that factor of I. And then we're going to have to make sure to rationalize the denominator. So turn the denominator into a rational number. So if I have the square root of 75, negative 75, over the square root of negative 3, that gives me I square root of 75 over I square root of 3. The square root of 75 can be simplified because 75 is 25 times 3, which is 5 times 5. So I can pull out a factor of 5. That means I'm going to have 5I square root of 3 over the square root over I square root of 3. Now, the first thing I want to do is I need to rationalize this denominator. So I need to get the radical, the irrational part, out of the denominator. I'm going to do that by harnessing the power of 1. Remember when we were trying to find equivalent fractions, we would multiply the numerator and the denominator by the same thing? So for example, if I had 1/2 and I wanted to find an equivalent fraction, I could multiply it by 2 over 2 and I'd get 2/4, where these are equivalent fractions. In this case, I want to multiply by something that's going to cancel out the square root of 3. So I'm going to multiply by the square root of 3 over the square root of 3. That gives me 5I square root of 9 over I square root of 9, which gives me 5I times 3 over I times 3. So I have 15I over 3I. And then I can simplify. The i's are going to cancel. 15 divided by 3 is 5. So this is our final answer, 5. Next, I have the square root of negative 32 over the square root of 8. The first thing I want to do is rewrite this as I square root of 32 over the square root of 8. Then I need to simplify what's under my radicals. Okay? If I have the square root of 32, that's the same as 2 times 16, which is 4 times 4, 2 times 2, and 2 times 2. So I have 2 perfect squares in there. So I'm able to pull out a factor of 4. So that's going to leave me with 4I square root of 2. Okay? Let's remember why I can do that. If I have the square root of 32, I can rewrite this as the square root of 2 squared times the square root of 2 squared times the square root of 2. And I can pull these radicals apart. That leaves me square root of 2 squared times the square root of 2 squared times the square root of 2. Remember that square roots cancel squares, right? This is like saying I have the square root of 4 times the square root of 4 times the square root of 2. So I'm left with 2 times 2 times the square root of 2, so 4 square root of 2. But I had an I out in front, so I got to make sure to multiply by that I. Now the square root of 8 is going to be 2 square root of 2. Let me show you how I got that. 8 factors into 2 times 4, which factors into 2 times 2. So I have 1 square in there. I can rewrite the square root of 8 as the square root of 2 squared times 2. That leaves me with the square root of 2 squared times the square root of 2 equals square root of 4 times the square root of 2, so 2 square root of 2. Now, if you know what you're doing, you do not have to write down every single step. You don't have to show me every step. I'm just making sure to write it out this way so everybody stays on the same page. So now I have 4i square root of 2 over 2 square root of 2. And I need to rationalize the denominator. But I'm not going to multiply by the whole denominator. I only need to multiply by the radical part, which is the square root of 2 over the square root of 2. So I'm left with 4i square root of 2 times 2, which is 4. 2 square root of 2 times 2, which is 4. So I can simplify this to 4i times 2 over 2 times 2, because the square root of 4 is 2. So I have 8i over 4, which I can simplify to 2i. So now we've multiplied the complex numbers. We've divided complex numbers. Let's talk about adding and subtracting complex numbers. So if I'm working with a complex number, it's typically going to be in the form a plus bi, where a is the real part and b is the imaginary part. We call these complex numbers. They've got a lot going on. They're both real and imaginary. It's very meta. Okay? So let's go ahead and talk about how we would add these. So when we're adding and subtracting complex numbers, we're going to add the real part and we're going to add the imaginary part, right? We can kind of think of them, this I, as a variable, okay? Because if we were to say be adding these two terms right here, we would be combining like terms. So I'd get 2 plus 6, which is 8, and 3x plus 4x, which is 7x. So let's go ahead down here. I have 2 plus 6 and 3i plus 4i. That gives me 8 plus 7i. And we always want the real part first. So it's really just like combining like terms. It's just like that. So here I have 4 plus 3 plus a negative 6, so minus 6, plus 2i minus I plus 3i. We're adding all of these. So 4 plus 3 gives me 7. 7 minus 6 is 1. 2i minus I is 1i, plus 3i is 4i. So I'm left with 1 plus 4i. It's really like combining like terms. Just remember that whereas x can stand for any number, I only stands for the square root of negative 1. Big difference. Okay, now we're going to be subtracting. Remember, just like when we're working with binomials, not complex numbers, we have to distribute this negative. So I have 6 plus 5i minus 3 minus 2i. That's going to leave me with 6 minus 3 plus 5i minus 2i. So I'm left with 3 plus 3i. Let's try that again. I have 7 minus 3i minus 8. Two negatives make a positive, so plus 6i equals 7 minus 8 minus 3i plus 6i. So I am left with negative 1 plus 3i. When I'm multiplying complex numbers, we're just going to be distributing or foiling in this case, right? This is going to be FOIL. This one we're just going to need to distribute. And this is just like when we were working with monomials versus a binomial or two binomials, right? We have to distribute. So I have 4i times 2. That leaves me with 8i. And then I have 4i times 3i, which leaves me with 12i squared. Friendly reminder, I squared equals negative 1. So I'm going to want to substitute that back in. I don't want to see any I squareds. So I have 8I plus 12 times negative 1. That gives me 8I plus, oops, not a plus, 8I negative 1 times 12 is negative 12. But remember, I want them all to be in the form A plus BI, where A is my real part. So I'm going to rewrite this as negative 12 plus 8I. Wonderful. So the next thing we're going to do is FOIL. It's still the same. First, outer, inner, last. So this is going to give me 12 minus 6I plus 20I minus 10I squared. I'm going to give you guys a second to make sure you FOILed that properly. I can combine like terms. I have 12 plus 14I minus 10I squared. But remember, I squared equals negative 1. So I have 12 plus 14I minus 10 times negative 1. That's going to give me 12 plus 14I minus 10. So I can simplify this to 2 plus 14I. Sorry, this is going to be a positive 10. So 12 plus positive 10 is 22 plus 14I. I'm going to do this next example so we have in a different color, so we have a better clarification of where this problem stopped. So I'm going to FOIL this. First, outer, inner, last. That leaves me with 2 minus 10I plus 3I minus 10I. Minus 15I squared. Let me erase that for clarification. Okay, so now I can combine like terms. I have 2 minus 7I minus 15I squared. Remembering that I squared is negative 1. So I have 2 minus 7I minus 15 times negative 1. So 2 minus 7I plus 15. That leaves me with 17 minus 7I. Remembering always to have our real part before our imaginary part. Now when we are dividing complex numbers, we want to multiply by the conjugate. Okay, so the conjugate of any number, of any binomial, of any complex number, let's say I had 3 plus 2I, the conjugate is going to be 3 minus 2I. If I have negative 1 plus 4I, its conjugate is going to be negative 1 minus 4I. See, I'm changing the sign. And the reason we want to multiply by the conjugate is because if I was to FOIL these two together, I'm going to be left with a real number, right? This is the sum and difference of squares. Our middle terms, our i's are going to cancel. So let's take a look at how this works. So if ordered to divide these complex numbers, I want to multiply by the conjugate of the denominator. That's really important. Multiply the conjugate of the denominator. Okay, so our denominator here is 5 plus 2I. So I'm going to take 5 minus 2I over 5 minus 2I. Remember, we're harnessing the power of 1, right? We're trying to also get the radical, because I is a radical, out of our denominator to rationalize our denominator. So let's go ahead and work this out. This gives me 8 times 5 is 40 minus 16I plus 45I minus 18I squared all over 5 times 5 is, 25. 5 times 5 is 25 minus 10I plus 10I minus 4I squared. So let's go ahead and combine all of our like terms. I'm going to go over here and write that out. That gives me 40 minus 12i minus 18i squared, which is times negative 1, over 25 minus 4 times I squared, which is negative 1. That's going to leave me with 58. This is a 45, not a 4. So that's going to give me 16 plus 45, that's 29, positive 29i. So I have 40 plus 18 plus 29i over 29. 58 divided by 29 is 2. 29i divided by 29 is I. So we multiply by the conjugate in order to make sure our denominator is left as a whole number. Here. Now if I just have I, it has a conjugate of negative I. So I'm going to go ahead and write this as 1 plus I over I times negative I. That equals negative I minus I squared over negative I squared. So I have negative I minus a negative 1 over a negative 1. That gives me negative I plus 1 over 1. So I have negative I plus 1, which I will rewrite as 1 minus I. So my real part comes first. One cool thing I want you to keep in mind is that knowing that I squared is negative 1, that means I have I cubed as I times negative 1, so negative I. I to the fourth is I squared times I squared, which gives us negative 1 times negative 1, which is 1. So what do we think I to the fifth would be, right? I to the fifth would be 1, so I to the fourth, times I, which is just I. So this is cyclical, right? I to the first is I to the second is negative 1, I to the third is negative 1, and I to the fourth is positive 1, and then I to the fourth is I. This is a really cool thing, because then we would have that I to the sixth is I squared, which is negative 1. I to the sixth is I to the fourth times I squared, which is 1 times negative 1, which is negative 1. So we go through this cycle. It goes I, negative 1, negative 1, negative I, 1, I, negative 1, and keeps going and going and going. So if I have I to the fourth, it might be kind of fun to think about ways I could break that up. So 12 is divisible by 3, and it's divisible by 4. And I know that I to the fourth cubed is I to the 12th, right? So I can figure out that I to the 12th, since I to the 12th is I to the fourth times itself 3 times, that's really the same as 1 cubed, which is 1. If I have I to the ninth, I know that's I cubed. I cubed is I cubed is negative I. So that gives me negative I cubed if I substitute in, which gives me negative I cubed. Well, I know that I cubed is negative I. So I have negative I, which is just going to equal positive I. So that's something kind of fun to play around with, working with I all by itself, as it does follow this cyclical pattern. So if I have I squared equals negative I, let's go ahead and work through some of these if I was to say have negative exponents. Now let's remember that I do not like negative exponents, right? So if we have a negative exponent, we want to make them positive by putting them in the denominator of a fraction. So now I have 1 over I squared. Let's keep in mind that I squared is negative 1. So that gives me negative 1 over 1 a positive 1 over a negative 1, which is negative 1. Next, I have I to the negative 1, so that just gives me 1 over I. But remember, we do not like radicals in our denominator either, right? Because I is the square root of negative 1, so it's a radical. So in order to eliminate the radical, I need to multiply by the conjugate. And the conjugate of a positive I is a negative I. That leaves you with negative I over negative I squared, which is negative I over over negative 1. Let me rewrite that. Which is negative I over, be good to have my pencil back. So I have negative I over negative I squared, which is negative 1. 2 negatives make a positive. So I have negative I over 1, which equals negative I.